Okay, so today we're going to be finding the coefficient of static friction, otherwise known as mu sub s, between the brick and the wood on an inclined plane. So first, we need to draw a free body diagram, as always, between the incline, which is the wooden plank, and the ground or the table. And there's theta, which is the angle between the two. And now we're going to draw the brick on the inclined plane with its center of gravity right here. So now let's draw the forces acting on the brick at this moment. So we have the force of gravity directly downwards. We have the force of friction opposing the motion down the incline. And we have the normal force. So now, since 2 out of 3 of these forces are not laying directly on our ordinary xy axes, what we're going to do is we're going to adjust the xy axes for this problem to be in line, so the x-axis lies along the incline. So now we need to break the force of gravity into its x and y components. So we have force of gravity in the y direction and force of gravity in the x direction. And now, because of basic geometry, theta here, this is also equal to theta between the force of gravity in the y direction and force of gravity. So now we need, because static friction means that it's no longer, means that the brick is not moving. We know it's in equilibrium, so we need to adjust our forces accordingly. So net force in the x direction equals 0, and the net force in the y direction equals 0. So let's color code this just to make it a bit simpler. So obviously we need to keep the components separate. So let's first work with forces in the x direction. So we have, gotta make sure that's static friction. We have force of static friction and force of gravity in the x direction. And since they're opposing each other and they need to add up to 0, we know that because of algebra, they're just equal to each other. So f of g in the x direction equals f of x. So let's say x components here. So we also know that f of g in the x direction is equal to fg times sine of theta. So let's write that out, fg sine theta. And we know that friction equals mu times the normal force. So we have mu static for static friction times the normal force. So now let's work on the y components. So in the y direction, we have normal force opposing the force of gravity in the y direction, which, similar to force of gravity in the x direction, we can break that into trig. So we have f of g cosine theta equals normal force. So now let's use systems of equation to solve for coefficient of static friction. So we have normal force right here and normal force right here. So now we can break this equation down to fg sine theta over coefficient of static friction equals normal force. So now they're both set equal to normal force. And we can set these two sections equal to each other because of the transitive property. And we have fg sine theta over mu sub s equals fg cosine theta. So now, because of simple fraction rules, we can say fg sine theta over fg cosine theta equals mu s, or coefficient of static friction. And now we can just cancel out the force of gravity in the numerator and denominator, and we have sine theta over cosine theta equals mu sub s. So now we know that mu sub s just equals tangent of theta, and there is our equation. And so now we know that theta is is the maximum angle that the incline will reach before the brick starts moving, and therefore we will plug whatever angle we find during the experiment into here and be able to find mu sub
To find theta, we conducted 5 trials where we had the brick on the plank of wood and a protractor at the base, and we would lift up the plank of wood up until the brick began to slide and then call out the angle the base was making with the table. On our first trial, we got a theta of 18 degrees, then 17.5, then 20, then 23, then 21.5, which means the average theta was 20 degrees. So to find the coefficient, we had to do tangent of 20 degrees, which is equivalent to 0.364, which means that the coefficient is 0.364. And so obviously that's not perfect considering how big of a range we had here. So the range, to be exact, was 5 degrees, because 18 was the minimum value and 23 was the maximum value. So I would guess that that means that the error could have been either 2.5 above or below where it should be, because if the overall range is 5, then you'd guess the average would be in the middle. So it could be 2.5 above or 2.5 below the actual theta. So that means that our error percentage should be about 2.5 degrees over 20 degrees, which is 12.5%. The error naturally came from just the delay in the time it took for the brick to start sliding, the person up top to say it was sliding, the person at the base to then check the angle and then call it out, and just the whole delay between the two. So the way we would fix that is by doing just a ton of trials, because theoretically, if we did an infinite amount of trials, we would get the right angle. So the more trials, the closer to the correct value for theta, but I think we did pretty well.